Hello everyone, it's me, Billy Younger again. I'm here to teach the lab for today. Today we're doing the the nonlinear graphing one lab. But I've also noticed some problems when my class was doing it yesterday, face to face. They didn't get something, so I'm going to go a little bit more in detail on this explanation so I can help my students that are already taking it. And also, I'll of course give them that data because they might have made a careless mistake in that. In addition to that, I'm going to recap some issues regarding propagation of error, which was a lab I think I did 1 or 2 weeks ago. But I give everybody a full 2 weeks. But it seems like some people don't necessarily didn't necessarily understand the process. So I thought I'd give you a few examples of how error propagates. I'll do that with my iPad. But I think first we need to go over the lab for this week, which is the nonlinear graphing one. So let me start by sharing my screen. I got to make sure I share the right screen, of course. So here we go. So this is our nonlinear graphing one lab. It is this week falling on lab seven, so it is lab seven. It's not always that the title will match, by the way, so just keep that in mind, especially with the online classes. But we also change the order from time to time in the face-to-face classes as well. So it's not unusual, is the main thing I'm saying, for it to be called in the document lab seven, where the turn-in right space might actually be called lab eight or nine or even four or whatever. The main thing is just make sure you get the title right, and that is included in the turn-in area. So the lab we're doing, like I said, is nonlinear graphing one. For you guys, you're doing it online, so we actually have a addendum, and I think I can still find a link to the video of the data that we're using being taken. But either way, the main thing is you need to be able to access this Word document. Remember, in our lab setting, you normally download the document and then you fill it in. If you fill it in with electronic type, you need to make sure you change the font color to something other than black so that I can easily see what you've put in versus what was already in the lab. Uh, of course, any handwritten stuff, you can write it right on there, no big deal. Or you can take photographs of handwritten stuff and insert those. You can also take photographs of type stuff, but sometimes those photographs, when you insert them, if you do things kind of smoothly, then it might even be obvious that, or not obvious that the typeset was part of the lab or not part of the lab. So if those cases are going to occur, then you probably should make sure any typesetting that you do or any typing you do in another document, take a photograph of, that should also be in a font color other than black. Just because, like I said, there are ways where you can insert photos and basically it's like a fade of the edges and it just looks like part of the original document. So if you ever have anything that's written with the typeset, but the it's not obvious that it was inserted, then you need to make that color font other than black as well. So what we're doing today is nonlinear graphing. We've talked to you numerous times. We did linear graphing one, we did linear graphing two. Both of those were cases where variables didn't necessarily automatically lend themselves to a linear representation. For instance, y equals mx plus b. That's a linear representation, y being the dependent variable and x being the independent variable. And it's called y versus x for a reason, because the y versus x means y is the dependent variable and x is the independent variable, and therefore x is on the horizontal axis and y is on the vertical axis. So that's just some stuff you're supposed to already know, but you might forget from time to time whether it's y versus x or the other one. I'm trying not to say the other one so you don't get that in your head as if it's something that really is factual. So, anyways, the opening theory talks about that. When you make a graph, for instance, you look at this one. This is clearly, well, you might think this could be a straight line, and in which case it'd be a straight line, sort of like this, maybe. But the fact that I've got like three on one side and then these other two on the other side, and they look sort of curvy, that's a good indicator that it's not a linear graph. If you look down here, it gives you some very specific intelligent guess strategies. It says, here's some of the equations that we run into in everyday life. This is one of our kinematic equations. It's actually the x equals 1/2 at squared plus v0t plus x0. But in this case, it had zero initial velocity, so the v0t term is not there. And it had zero as the initial position, so the x0 is not there. And we've changed the final position to just represent the distance traveled d. V. This is another kinematic equation, but this one again is a case where the initial velocity was zero. This would otherwise be called or be written as V squared equals V zero squared plus 2 times A times parentheses X minus X zero. But just like over here, we made the X into D and we called the X zero zero. And also we let V0 be zero. So V0 was zero, so we don't have that term in there at all. This is Kepler's one version of Kepler's third law. Kepler's third law specifically says the square, which meaning if you square both sides of this equation, you would get t squared equals some constant k squared because you square both sides as different constants. So you have to call it k squared if you're sticking with the original constant times r to the third power. And that's really the way he stated it is the square of the period is proportional to the cube of the semi-major axis. And the semi-major axis pretty much plays the role of the radius of the orbit, sort of. But it's talking about elliptical orbits, which elliptical orbits don't have radii. They have a minor axis and a major axis and a semi-minor axis and a semi-major axis. The major axis being the long distance from the one end to the farthest away other end. That's the major axis. Half of that's called the semi-major axis. And the short side is the minor axis, and half of that's called the semi-minor axis. So again, that's where that's from. Here's one for a pendulum. This is the period of a pendulum. T is equal to 2 times pi times the square root. Notice the exponent of 1/2 means square root. So it's t, the period, is equal to pi times the square root of L over G, where G is gravitational acceleration and L is just the length of the pendulum. That's one we're going to be curve fitting potentially as well in this lab. It gives you some nice linear regression analysis thoughts and explains that. What we find in nature is that generally the standard guesses are exponential powers of plus or minus all of these values. So you can say plus or minus 1/2. So that's 1/2 would be times the square root of X. Minus 1/2 would be over or divided by the square root of X. Minus 1 or plus 1 is another one, but obviously the plus 1's just basically y equals mx, or maybe y equals mx plus b, so they didn't even list the plus 1 for obvious reasons. But you could do plus or minus 1.5, which is 3/2, which we just saw in the one way of writing Kepler's third law. It's also plus or minus 2, plus or minus 3, and that's pretty much all they tend to be. It's very rare that you learn of one that's, you know, zero point 0.3 as the exponent, or zero point 0.7 or 0.25 or something. Well, 0.25 might not be bad. I've seen a 1/4 before. But anyways, it's normally, yes, a rational number. You could try 0.97 or 2.1 like it says, but you really want to resist that temptation because generally we have not found nature to be such an oddity. It's normally been these powers. And in fact, if you go to curve fit a graph that uses one of those powers and you find that you can get a better R value for your curve fit just by changing from 1 to 0.97, that's what the author of this lab is telling you, is resist that temptation because you expect a little error in both labs, period, or in both graphs, period, no matter if it's exactly the right one or the one you're using. So if your theory calls for it to be, for instance, negative 1/2, and you find that negative 0.2523 is better, that doesn't necessarily mean 0.2523 is really the proper fit because both of them, as I said, both graphs should actually have error. And you might be getting rid of some of the actual experimental error by choosing an errant exponent instead of the exponent it should be. So it's better to get a slightly smaller or slightly, yeah, smaller R value on your curve fit that's consistent with the theory than almost the same size R value for one that's better consistent, but doesn't fit any theory that we know of. Because as you probably, hopefully know, is if I'm teaching it from a textbook, this has been tried and true. We don't make places in physics by going on assumptions that we haven't verified. So me teaching you these kinematic equations and this period equals 2 pi times the square root of L over G, that's all been tested. So obviously the theory is acceptable, and as best we can tell, it is correct, at least to the number of decimal places that we've been dealing with to date. So keep that in mind. It does say comparison here. It does tell you that generally what we try to do is just put one exponent on one variable, and specifically the author of the lab as well as myself personally, we generally prefer the variable that's raised to a power to be the independent variable. So the one that you plot on the horizontal axis should be the one that you raise to the A1 power, and that's what this whole thing's talking about, is the A1 method and stuff of that sort. So there's the A1 method. So what you do is you make a table of data. For instance, in the case of object and accelerated motion, you could say t in seconds is a data point, and if you're going to make d on the vertical axis and t to some power on the horizontal axis, then what you do is you put in cell A1 of Excel, you put in a number like any one of these. So you could put in positive zero point 0.5, you could put in negative zero point 0.5, you could put in negative 1, you could put in plus or minus 1.5, plus or minus 2, or plus or minus 3. Each of those can be tried in the A1 cell, and this column right here would be made of this variable. So you type in it first, as this might be column B, row 3. So you'd put equals B3, caret symbol, dollar sign A, dollar sign 1, and then you pull that all the way down, and that would make the data for all of those raised to whatever A1 power. Now, the beautiful thing about that is each time you go up here and change cell A1, you get to change the way the graph looks. So if you make the graph, it'll actually change it in real time, and you can look at the data that way. Uh, there's another one with electrostatic attraction, and this one they've given you the data just like they did in this one. They gave you the data, and in Kepler's third law, again, they gave you the data. So your job is to plot all those as well as the orbital velocity, and you're ultimately looking for in all these cases, because you have to find the right variable A1 for each case. You're going to then do the curve fit using Excel, and in principle, you could have used Logger Pro too, since you have access to that, but we're just going to use Excel. But it'll spit out the equation because you set that up in the trend line setups, and you look at the equation, which will say something of the order of y equals some constant times x plus some other constant. That constant multiplied by x, of course, is the slope, so it goes here. That constant that's added to the x term all by itself, that's a pure number, and that should be the intercept. And then you can write out the actual equation right here, but not use the normal generic y and x. You're going to specifically use, for instance, d as in place of y, that's capital D, and then in place of x, you're going to use t to whatever power you found was best. Now, you might find a couple of different graphs or a couple of different A1 values that are sort of equally good or are really good and hard to decide between. If you do that, I'm never going to take off for you giving me more of the information than asked for. Like this one does not ask for the graph, but I want to see the graph you chose. And if there was any controversy as to which graph is better, I would like to see, all the graphs that you're considering for each other, and you paste them all right after this line. This blank line where you put in the equation, you could paste all the graphs in there, make it big enough so that I could see the actual equation that it's putting out as a trend line, the r squared value, and the data values on the vertical and horizontal axes. So if that means you're taking up extra pages, that's okay, because remember, I'm not even requiring you to print this out. It's all going to be in electronic format. So having a little extra space is just fine. Here's the one for electrostatic. Again, they gave you the data. Oops, did not mean to do that. Let's open that back up. So here's the data for the electrostatic one, for instance. And that one, you're basically trying to learn how the force is related to the distance of separation between, say, two objects. And therefore, you're trying the distance r, that's going to be your variable that you put on the x-axis, and your force in newtons is F, and that's going to be put on your y-axis. And your A1, again, will be one of those special values until you find the one that makes a really good fit and happens to be one of those rational A1 values. Okay, remember rational means can be expressed as a ratio of two integers. That's what makes a number rational. Irrational numbers like pi or like the square root of 2 or the square root of 3 are not rational ones. So you would not in general expect an exponent of pi, but I will tell you in physics we do sometimes get exponents of pi and exponents of the square root of 2 and weird stuff like that. But anyways, there's your Kepler's law one, and there's your orbital velocity one. And then finally, they're wanting you to take some data for the inclined plane. I shouldn't say finally, but now they're also wanting you to take some experimental data for an inclined plane. What you'll notice in the addendum is we actually gave you that data, but this is the data that it seems my students are making mistakes. Some of them actually got really good G values, which tells me they knew what they were doing and did it correctly. If you got a G value that had a G meaning 9.80 meters per second, if you did a curve fit and properly solved for the parameter in that curve fit in that trim line, and properly solved one of those parameters for G, and you got G just a few percent off from 9.80 or 0% off, then chances are you did it correctly. But if you're off by more than especially more than 10%, there's probably something you did wrong. Okay, so I just want to make sure everybody's aware of that. In general, in our labs, we are always getting less than 10%. Occasionally, like there's a really tough experiment we do, and we don't have that many data points, and the results, therefore, might come up to plus or minus 9% or even 11%, and that one we would accept. That's in the magnetic deflections lab of the 242 course. But in general, if you got more than 10% error in any of our physics labs, it's probably something you did was done improperly. So keep that in mind. So again, like I said, this is the inclined plane. What they were actually having you do is set up a cart on an inclined plane, and they basically took the linear air track, the 2 meter linear air track we have, and we take and put a block of wood under one leg, and that causes it to be an inclined plane. And then we start from some reference point and allow it to go a certain distance until it hits the photo gate. The instructions tell you exactly how it was done, and the video, if I can find that link, will show you how it was done as well. But the main thing is, as the cart gets down the inclined plane, it encounters the photo gate, and there's a little flag on top of the cart. That flag was supposed to be a little piece of cardboard, like an index card or something like that. That's about 5 centimeters wide. In my lab, I actually, gave out these little pieces of index cards, and the student was supposed to measure the width of that. And then as that blocked the photo gate would start timing, and then as soon as it was unblocked, meaning the whole flag had passed by, it would stop timing. So it gives you basically how much time it takes, let's say a 6.37 centimeter flag to traverse the whole length of the flag through the photo gate. That allows you to determine the velocity at that point. That is not the time that you're going to be graphing. It shouldn't be the time that you're going to be graphing, because it's literally that's just a small part of the time that was required to be taken over. Man, that phone call just messed me up. But anyways, that was a small portion of the time that was just supposed to be referenced to reference your ability to determine the velocity at that endpoint. So what you were really looking at is using that small time interval to figure out what the velocity of the cart was at the end of the trip. So in one case, it might go down 10 centimeters. In another case, it's going to go down 20 centimeters. In another case, it's going to go down 30 centimeters and 40 centimeters. But in each case, it's going to traverse that last 5 centimeters in a certain amount of time. And you would imagine if it only fell down a 10 centimeter incline, the velocity would be very small. But if it fell down a 20 centimeter incline, it would be faster, and a 30 faster still, and a 40 faster still. And therefore, that is what you're supposed to be making use of. So make sure you know how to properly use that. Chances are, if your G value did not come out right, you did it wrong. So check on that. But here's where it tells you the step-by-step procedures. You can see the inclined plane with the little flag, and it even tells you that what we were supposed to do was slide the cart along the inclined plane right until the flag just barely blocks out the photodetector. Okay, that is where they're telling you exactly how to reference 10 centimeters versus 20 centimeters versus 30 centimeters of falling distance. And you're going to do the right here. You can see 10 centimeters, 20 centimeters, 30 centimeters, 40, 50. And of course, if you ended up doing it in such a way that you couldn't get exactly 10 centimeters, it's perfectly okay to scratch through the 10 centimeters and call it 9.82 or something. But the big thing is, you should be able to get to two decimal places using meter sticks or a regular ruler that has 10 intervals in between 1 centimeter and 2 centimeters. You should still be able to use two decimal places on that, and therefore get in this case it would be, if you're keeping it in centimeters, it would be 4 sig figs. So that's very reasonable. And what we did was we did it 3 times. So we would let the object, the cart, slide down the incline, which again I'm saying slide, but it's really a nearly frictionless incline, so it's really just hovering down the incline. And after 10 seconds, or after 10 centimeters, it's going to measure the velocity at the end of that 10 centimeters, or allow you to measure that velocity. It's going to just measure the amount of time it takes that flag to pass through the photo gate at the end of the 10 centimeters. So you put that time right here, and then you do another trial and you put it right here, and you do another trial and you put it right here. And then you take the average of those three, and that should give you the time, which is again related to the velocity. Okay. So on the spreadsheet, plot time on the y-axis in seconds and distance on the x-axis in centimeters, but you got to figure out exactly what it is that you're interpreting there. So I'll let you go on with that. There's also a pendulum part. We would normally do that pendulum in class, and you can certainly do it that way. For instance, there was a video that we showed before that allowed you, but in this case, we're actually changing the length of the pendulum to 5 different measurements. Okay, so what we've done for this part of the addendum is we're just allowed you to go to a physics simulation website where you can make the pendulum what you want and then measure the periods and then take the average, all that good stuff. So that's what this lab is. That allows you to calculate G as well, because you know the period T is supposed to be 2 pi times the square root of L, and then, of course, you could say all of that's divided by the square root of G. That's sort of a better way to think of it. So you can realize that the square root of L, in theory, should be what you were plotting on the horizontal axis, and the period should be what you're plotting on the vertical axis. So hopefully that's a pretty good hint. Now let me switch over to the addendum. I think I can still do that just by changing my tabs. And yeah, it looks like that's fine. So here's the addenda. It says, watch the video to see how the data was gathered for the inclined plane. Keep this lab as specified in the lab book, but use the data below for the inclined plane. You will then use PHET simulation to gather your own pendulum data. So here's the times. And remember, those are the time intervals that it took for the little flag to go by. That is not the time it took for it to fall 10 centimeters. It's the time that the little flag took to completely pass by the photo detector, and therefore you can use it if you know the width of the flag to, for instance, find the velocity. But you're in this case, they're actually specifically telling you to plot time and distance, and then that should have some hallmark or some relationship with it. Here's the website that you could just click on to get to the simulation website, where you can make a pendulum of whatever length you want, and then you can find the time it takes for 10 oscillations, and then you divide that by 10 to get the period, so on and so forth. So that really is the main part of the lab that we're doing this week, and of course it'll be due by 11:59 p.m. on Tuesday next week, which I believe is the 11th of May. So just keep that in mind. Now that we've done that, I want to stop sharing, and I'm going to go back to our propagation of error stuff to talk about that. It's now 12:38, and that's normally the time where students are supposed to be logging in if they wanted this for an office hour. I haven't seen anybody yet, but I'm going to continue with this, and then when I'm finished, I'll take open questions if anybody's here. So this time I'm going to actually share my iPad screen with you instead of my desktop. So let me do this, advance. And now I click share, and it should come up in a few, but it takes a couple seconds for it to connect and all that good stuff. Okay. So this is about propagation of errors, just in case no one knows the word that I'm using there, because that's not a word people use too terribly often. It's propagation, P-R-O Propagation of error. I could have put that all in caps. Of course, it doesn't really matter too terribly much. But the main thing is we're talking about propagation of error. And what I gave you in the propagation of error worksheet was that when you have a function of one variable, in other words, you're using a formula to take a variable like x and compute a new variable called f. Okay. So you could say y equals f of x. What I'm meaning is this formula might be something as simple as y in meters is equal to, let's say, 1 meter over 100 centimeters times y in centimeters. Okay, so that could literally be a function. We would literally be saying uh, f of x is equal to 1 meter per 100 centimeters times x, like that, and that would be our function of one variable. I could have used it as y's as I did it immediately above it, or I could have used it as x's. Doesn't really terribly matter. I could have even just called the left hand side y in meters and the right hand side x in centimeters. All of that's fair. But the main thing is if you do have to take a variable like x, which has an uncertainty, so it would have what we call a best estimate of x, which can be either written this way or sometimes they'll just write it that way, and then plus or minus some error in x. That's the way values are recorded when they're reported from, for instance, a lab or something like that. So if you had that variable x, which is given by x bracket or x bar, plus or minus some uncertainty in x, which we call sigma x, or the standard error of x, then how does that error sigma x come out after you use a function like f of x? So just let me remind you, this is the best estimate of x, which normally means the average. As we learned last time, though, if you're really doing some serious work, you might actually have individual errors associated with each trial, in which case you might actually have to actually calculate a weighted average as opposed to a just a straight average, and that's fine. It's no big deal. It's just another level of calculation. But I'm not going to make you do that in my course ever, basically. This quantity right here, sigma x, is technically called the standard error, which again we introduced you to in the propagation of error lab. So this is called the standard error, but it's also called the standard deviation of the mean. I would also say that this is the best estimate too. That's why I wrote it below it. So what we could say is, just like I did here, the function f of x is equal to 1 meter over 100 centimeters times x. And this is with the understanding that this quantity is measured in centimeters. Okay, so that's what that means. And this quantity comes out in meters. Okay, so how do we handle a one variable function? Well, we've already told you that the uncertainty in, actually, let me switch to blue again. The uncertainty in f is equal to the derivative df over dx times the uncertainty in x. And notice I have absolute value bars around it. So if you look at f of x equals 1 meter divided by 100 centimeters times x, then df over dx is just going to equal 1 meter over 100 centimeters. That may seem a little weird, but that's mainly because you're not used to dealing with units as coefficients of numbers. You should be getting used to that a little bit now from just being in the physics course as long. But anyways, that's what it is. And there's no way that can be positive or can be negative. So the absolute value of df dx is just the same value. So when I write absolute value df dx, that's just equal to 1 meter over 100 centimeters. Okay, so for instance, if our value was x is equal to 5.23 centimeters plus or minus 0.03 centimeters, I want you to notice for starters while I'm doing this that this digit is the instrumental, or it could be the instrumental error, but the main thing is it's the error that we've assigned to the variable x. Okay, that could have been by you taking 100 trials and you took the standard deviation, and you took the mean, of course, too, and then use that to calculate the standard deviation, and then use the standard deviation to calculate the standard error, and 0.03 was the answer. But it could also have been the instrumental error with the device you were using. Maybe that had an error of 0.03 centimeters. And when you actually did multiple trials and you calculate the standard deviation or standard and then the standard error might have come out to be 0.02 or 0.01. Well, you can't use statistics to make your experiment better than it was. So if your device had an uncertainty of 0.03, then that's what goes there, even though we normally use the standard error. So keep that in mind. So, if we wanted to find out what f of x is, then, oh, that was the other thing. I said this 3 is in the exact same place as the last digit of the best value. That's always the case. That's the root of what we use in lieu of significant digit rules. We do our calculations, we take our best estimates of the values, and then we round them according to the uncertainty that they had. And that uncertainty, like I said, could be instrumental uncertainty, or it could be a calculation of standard error, or as you'll see in a second, it could be a propagated error that you got through using the propagation of error techniques that I'm covering now. So in this case, if we wanted to know what f of x was, so uh, we would say f of x, which you normally just call y, but I'm calling it f of x anyways. F of x would be 1 meter over 100 centimeters times x, where we're going to actually put in the x value, which is the best estimate. So that's 5.23 centimeters. And that would put out 0.0523 meters. So that's how the function works. And if you wanted the uncertainty, you would say the uncertainty in f is equal to the absolute value of the derivative of f with respect to x times the uncertainty in x. We've already computed what the absolute value of the derivative of f of x is, and that was 1 meter divided by 100 centimeters. And then the uncertainty in x is, of course, 0.03 centimeters. And now what you can see is this becomes 0.0003 meters. So now we could say that f is equal to some best estimate of f plus or minus the uncertainty in f. And we've got all the stuff we need to do that, so we can now say that f of x, or we could just call it f, either one, is actually going to be equal to 0.0523 meters plus or minus 0.0003 meters. So the 3 lines up in the first, second, third, fourth decimal place. And notice the uncertain, or the actual f value, which is 0.0523. That 3 also is in the fourth decimal place. So you see that it at least is consistent with what we're teaching you. Specifically, the error should allow 1 digit of error, and that should be the place where we round off the best estimate in that same decimal place. So we see that that works. There's no one here. I would normally ask for people if they had any questions, but I think that's a pretty good way of explaining it. And we're done with that. Now, for instance, in the lab that we were just talking about, we were given a unit of time. In fact, I can pull one of the actual units of time. We can say, for instance, for 10 centimeters for that lab, what we found was time one was 0.107 106 seconds. Trial 2 was 0.107 seconds. And then time 3 was 0.17001 seconds. So those are our three trials for the 10 centimeter mark. Our We're going to call this actually, your book is calling it T. Your lab report write up is calling it T. I think it's better to think of it as sort of a delta T. So I'm going to write delta T as that quantity. And what we're going to see is delta T is equal to some best estimate, which we can see is 0.107106 0.107106 plus 0.107000 plus 0.17001. That gives me 0.38416. So 384,116, excuse me. Now I'm going to divide that by 3, and my average is therefore 0.12803. I'm trying to make spaces here, so let me remind everybody, you always want to put these in pods of 3. So what I'm going to do is try to put a little bit more space in there so it's obvious that it's a pod of 3 numbers. So that number is 128, and then 038, and then 6. Whoa, put it back on the marker, and then 666, and then 7 seconds. That's what the average is. Okay, so this would be what we call either delta T bar, or it could be called delta T bracket, like that. That would be acceptable as well. But the main thing is that is just the time for that little flag to pass by through the photo gate at the end of the 10 centimeter run. The other data point, of course, would be the 20 centimeter, and they gave you 3 times for that. And then you gave you 30 centimeters, they gave you 3 times for that, so on and so forth. So if we wanted to, for instance, figure out what the velocity was, we would know that velocity is equal to delta x over delta t, and that would be our average velocity. But if we wanted it to be instantaneous, oops, I'll just abbreviate it. It's instantaneous was the word I want to write, so I'm just going to write it as instant. That is, oh, man, I hate when this thing just keeps changing into an eraser. That is the limit as delta t approaches 0 of delta x over delta t. Now, the delta x is supposed to be, that delta x is supposed to be the width of the flag, which your manual said was on the order of 5.00 centimeters. The ones I passed out turned out to be more like 7.53. So I'm going to say delta x is equal to 7.53 centimeters plus or minus 0.01 centimeters. That's what I would have gotten if I took, X number of trials of the width measuring the width with a vernier caliper, for instance, would have gave me 3 decimal places, but using just a regular meter stick only gave me two. So if I took maybe 10 measurements and then took the average and the standard deviation and then used the standard deviation to calculate the standard error, the zero point zero 0.01 would either be the instrumental error, which would be zero point zero 0.01, obviously for any device that's measured to the nearest tenth of a centimeter. In other words, it's marked with 10 spaces in between 1 centimeter and 2 centimeter. So those little individual marks each correspond to zero point 0.1, and then the next space is 0.2, 0.3, 0.4, and then that long line at the end of the next space is zero point 0.5, and then 0.6, 0.7, 0.8, 0.9, and then that long line is 2. So that was 1.1, 1.2, 1.3, 1.4, 1.5, which was longer than the zero point 0.2 and the zero point 0.3, but not as long as the 1 or the 2. And then 1.6, 1.7, 1.8, 1.9, and then 2.0. Okay. So if your device is measuring like that, then the instrumental uncertainty is at best point plus or minus 0.01. Okay. If there's some problem with it where the thing might not be that square or you're trying to measure across the distance that you can't access, you might need to call it instrumental error to be zero point zero 0.02 or zero point zero 0.03. And that's somewhat of a subjective call. But once you make that instrumental error hypothesis, you should write that down and record it. And then you go about taking the mean and then take the standard deviation and then take the standard deviation, divide it by the square root of the number of trials, and that gives you the standard error. If that standard error came up to be smaller than zero point zero 0.01, then you just have to use zero point zero 0.01. If it came up to be exactly zero point zero 0.01, you'd still use zero point zero 0.01. And if it came up to be bigger than zero point zero 0.01, maybe it was 0.012, you'd still use 0.01. If it's 0.014, you might choose to use both of those, but then you'd also have to carry one extra decimal place on the best estimate of the value. But again, that's only with the leading digit being 1 and the second digit being like 4 or 5 or 6. At that point, once you get to point 0.0017, for instance, you should probably just call that 0.002. Okay. Now, all of that, once you've settled whether the standard error or the instrumental error is big enough, once you've settled that, that's what you're going to put after the value of delta x. And therefore, the velocity using this formula for velocity and using, uh, well, that was really bad, but using this formula for velocity, which is the limit as delta t approaches 0, then what we get is V. Because the 5 centimeters is such a small distance and the time interval is such a small time interval, notice it's well under 2/10 of a second. So we, in some sense, already took the limit. So this would tell us that the velocity is going to be 7.53 centimeters divided by 0.128038667 seconds. When you do that, you get 7.53 divided by, and I'm just going to pull the same answer I just did, and I get 58.810,359 and 3.7. So that's the calculation that I got, and that gave me that many centimeters per second, which is on the order of 0.58, 0.588 meters per second. So that's a way you could actually calculate the velocity. But how do you find the error? Well, the velocity formula, v, which is a function of x and y, is actually equal to the limit as delta t approach 0 of x minus x0 over t, or actually it was not of y. I'm sorry about that. It was actually a function of x and t. So it's a function of x and t, and the final time is t, and the initial time is t0. So you can look at that as it. But the limiting process more or less became just the fact that we were measuring over a 5 or 7.53 centimeter distance. What was that number I used? Yeah, 7.53. So in principle, there it goes again, turned into an eraser. So in principle, all we really have to do is say that v of x and t is just equal to x over t. The propagation of error formula when there's multiple variables is the uncertainty in f, and this is f of x, y, z, and you could have any other number of variables, of course. That turns out to be equal to the square root of the partial derivative of f with respect to x squared times the uncertainty in x squared plus the partial derivative of y with respect or partial derivative of f with respect to y squared sigma y squared plus the partial of f with respect to z squared sigma z squared square root. So if v of x and t is equal to x over t as I wrote, then the partial of v with respect to x is just 1 over t because the t is acting like a constant. So if I had 1 over 4 times x, then the derivative of 1 over 4 times x would just be 1 over 4. So in this case, I had the function was x times 1 over t, and t is being treated like a constant, so the derivative of it is 1 over t. Similarly, the partial derivative of v with respect to t is really the partial derivative of some number x, which is just like we're treating it like a scalar, just a regular number, times 1 over t, so that's t to the negative 1. So we're just going to write the x because that's going to be out in front anyways, because that's just like a 2x. So the derivative, for instance, of 2x is just 2. So we had a derivative of 2 times 1 over t. That would mean the 2 has to come out front. Now we take the derivative of 1 over t. 1 over t is t to the negative 1, and the derivative of t to the negative 1 with respect to t is negative 1 times t to the negative 2. So I'm going to write negative t to the negative 2 power, which is going to be negative x over t squared. So that is our derivative with respect to t. So now our formula, sigma v, should be equal to the square root of 1 over t squared times sigma t squared plus, or excuse me, that one was x, sorry, so, oops, I didn't mean that. That was my derivative with respect to x, so this should be, dang it. So this should be the uncertainty in x squared plus the derivative of v with respect to t. That is negative x over t squared. That's got to be squared. Now I'd multiply it by the square of sigma t, like that. And that's actually a good formula. Okay, so we could actually calculate it accordingly, but I'm going to show you another way in a second. But right now I'm going to write down the square root. Now, how do we actually implement this? Well, the way we're supposed to implement this is put our best estimate for t and for x in. So our best estimate for t turned out to be the quantity 0.0 or 0.128038. So this is 1 over 0.128038. And you could go more decimal places if you wanted to, but I really don't need that many more. I've got 6 there, 6 decimal places there. Well, maybe it'd take to just add one more because the next digit was 6 and the next digit was 6. So I'm going to go ahead and round that. So this is in seconds. That quantity is squared. Our uncertainty in x turned out to be 0.01. So I want to say 0.01 centimeters. Now that's got to be squared. plus now we're going to take the negative of the x value, and our x value is 7.53, so it's negative 7.53 centimeters divided by t squared, which is 0.128038. That quantity that quantity is in seconds, and it needs to be squared down here as well. But then in addition to that, the whole value needs to be squared. And then we got to multiply it by sigma t, and we found that our uncertainty in t was, oh, we didn't actually calculate the uncertainty in t yet. What we would do to calculate the uncertainty in t is we take the standard deviation of those three numbers, which obviously is not very good, but we could take the standard deviation of point 12803866667, and I'm going to do that here in real time using a spreadsheet blank workbook right here. So what I'm going to do is I'm going to type in the numbers. The numbers are 0.17, or excuse me, 107,106. The next one is 0.107. And then after the 107 is 000. And then the next digit or the next number is 0.17, assuming I copied it right. 0.17001. Each of those are seconds. Now I can take the mean, which I've already calculated to be 0.128038667. I'm going to say the mean is equal to the average. That's what I type into Excel, AVERAGE. I type in equals average parenthesis, and then in the parenthesis I highlight the three cells, and it'll automatically take the average of those, and I get again 0.128038667, so on and so forth. I can also do the standard deviation, and that's equal to, I type in equals STDEV in parenthesis, left parenthesis, and then I highlight the three values. And I'm doing this in Excel, okay, so it's something you've done before. I didn't feel compelled to show you the window while I was doing it, but I'll pull up the window in a second. And I just got that the standard deviation for delta t, so t, standard deviation, let me write it this way. I'm going to say the standard deviation of t is 0.036 uh 34828. And then 28, and that's seconds. So that's the standard deviation in seconds. Of course, the standard error is the standard deviation divided by the square root of the number of trials. So I call that ERR, standard error. That's equal to the number, which was the standard deviation, divided by SQRT, which is the square root function. And then I write parenthesis, and obviously I only had three trials, so I'm just dividing it by the square root of 3. So that gave me a value equal to 0.020. So standard error is 0.020, and then 986. That's plenty of digits, even though I gave more before, but that also has units of seconds. So 0.020986 is supposed to be the standard error in the time. So I'll write 0. Actually, 0.209, or excuse me, 0.020. Sorry, I made a mistake on that one. 0.020, and then the next three digits are 986 seconds again, but that's going to be squared, and then I got to take the square root of all that. So this is how we actually go about calculating it. Uh, just to let you see what I just did, let me switch my share for a second, and I'm going to share screen instead of my iPad. So the screen that I would like to share is this one with Excel. And you can see that basically I just put in the time values 0.107106, 0.107000, and 0.17001. I think I actually copied those numbers. Nope, I did not copy them correctly, but that's okay. The 0.17 was the one that I thought I might have copied wrong, and sure enough, I did. It was 10701, I think. But either way, assuming those are the values, then all I had to type here was average B2 to B4, and that gave me the average that I had computed. And all I had to do to figure out the standard deviation was type in equals STDEV B2 to B4, and that gave me the standard deviation that I just told you about. And then all I had to do was take the standard deviation, which is what was in B7, and divide it by the square root of 3, because 3 is the number of trials I had, and that's where I got the 020986. So let's stop sharing there, go back to my iPad screen, and this should pop up in a second, and we'll finish our calculation. So what I'm going to first do is the very first term in the square root. So I'm going to take 1 divided by 0.128038 and I'm going to divide that. Oh, okay. Evidently, I typed a decimal by accident twice instead of a 0. So let me do this again. 1 divided by 0.128038. That gives me 1 divided by 0.1280387. That's actually 7.81013863. But now I got to square that, and that gives me 60.99. So 60.9982, say. That should be actually 83. The proper rounding is 83, not 82. But that's, of course, plenty of spaces, and that's in seconds squared times zero point zero 0.01 squared, which is 0.0001, and that is centimeters squared. And then the next term is 7.53. It's technically negative 7.53, but I know I'm going to square it, so it doesn't matter too terribly much. I'm going to divide that by 0.128038, and that number has to be squared in the denominator, so I'm squaring it. So when I got 7.53 divided by the square of 0.1280387, that gave me 459.3169. So y'all can, listen to this back and double check your calculations. But now I've got to actually take that and square it. So that number turns out to be 210,972.05, and that of course is centimeters squared per second to the fourth. And that's just the first part. Now I got to take 0.020986, and I got to square that, and that is 0.00044041 1, 2. And this is seconds squared. So that's the last factor. And of course, I got the square root of all that. It's got to be taken. So let me multiply the 60.99. So the 60.99. Okay, I was trying to steal it off my calculator screen, but it wouldn't let me. So I'm just going to do it the old-fashioned way. 60.9983 times 0.0001. This gives me the square root of 0.0060998 centimeters squared per second squared. That's the first term. The other term, I've taken 21097.05 and I'm multiplying that by 0.000440412. That should be enough for that, and that gives me, yeah, that gives me 92.91462, and that actually turns out to be centimeters squared per second squared as well, because the squared seconds in the numerator cancels out with the seconds to the fourth in the denominator. So now I got to take the square root of all this stuff. I'm really surprised at how big that number became. I'm kind of worrying that I should maybe test it to make sure. But either way, let's continue on. Assuming these numbers are correct, now I'm going to take this number, the 92.91, and add to it the point zero zero 60998.2, and I'm going to take the square root of that, and that gives me, this can't be right. There's some number that went wrong here. 9.639 and then 536 centimeters per second is the uncertainty in the velocity. Now the velocity did turn out to be what, 58.81 centimeters per second, and an uncertainty of 9 is kind of big, but what this entails is that we can now say our velocity is supposed to be our best estimate of the velocity, which we found was 58.810. Carry a couple other decimal places, 359 centimeters per second, plus or minus. Now, this sigma v is saying that should be added on the end, and that's just 9.6 centimeters per second, but we really should only have one digit of uncertainty, because if we know the uncertainty is 9 in the ones place, then our idea of our chance of knowing what the tenths place is nil. So we really should just call this 1 or 10 basically. So we would then say this is 50. Uh, I guess we'd have to actually call it 60, which is 6.0, which in other words, the zero shouldn't be there at all. So I just have to call it 6 times 10 to the 1 centimeters per second, plus or minus 1 times 10 to the 1 centimeters per second as my uncertainty. So you can see it's really not that good a result, but that might be a result of my erroneous calculation. Not really sure. I think everything was done more or less correctly, but again, just did it on the fly. But that's the way the propagation of error formula works. We can use the propagation of error formula to figure out sigma v, and then we round sigma v to one sig fig, and then that's where we have to record the last digit in the best estimate, which in this case turned out to be in the tens, TENS place. Okay, there was another way we could do it. Once we got this quantity, the sigma v equals 1 over t squared times sigma x squared plus negative x over t squared. So once I got that, there was another way I could have made it a little easier, and I'm going to show you that now. So it turns out a lot of times when you do this propagation of error calculation, it turns out the fractional error formula is often, when there's a lot of multiplication going on, the fractional error is often easier to write out and compute than the regular error is. So the fractional error is actually supposed to be sigma v over v. That's the symbol we use for it. But the formula for it is the uncertainty in v divided by the best estimate of v. Now that's equal to what we just found was the sigma v was sigma x squared over t squared, trying to make that a little more condensed to write it. We could also say x squared t to the fourth sigma t squared. Now, if I want to divide it by v, we know that the formula for v is x over t, so I can just put x over t in here. And then I can get it under the square root by squaring it. So I would have a big square root, and it'd be 1 over t squared sigma x squared plus x squared over t to the fourth sigma t squared. And now I'm dividing all of that by x squared over t squared. You can see, for instance, that the t squared here cancels out with the t squared here. And you could also see that the x squared here cancels out with the x squared here. So keeping my wits about me, I can finish up calculating this fractional error as follows. I get the x squared is going to stay on the first term, so I get the square root of uh, sigma x squared over x squared, and then the t squared canceled out, but the x squared's canceled out a little bit as well. So this one's going to be sigma t squared over t squared, because the t squared is going to cancel out with the t to the fourth, and the x squared is going to cancel out with the x squared. So we get that, and that's just a simplification of that is just the fractional error in x squared plus the fractional error in t squared. So that's a much simpler formula than the sigma v did. And now we can use that, of course, to figure out exactly what sigma v is. I'll show you that now just so you understand. So what we found was our v was 58.810 and then 359. That's more than enough digits, of course, and that's centimeters per second. And then our that was our v. What we had for our sigma x was our uncertainty in x was point. Where did I find it? Point zero one. So our uncertainty in x is 0.01, and that's centimeters. Actually, I wrote seconds there. And then our uncertainty in t we'll need as well. Our uncertainty in t turned out to be what we did our standard error on, and that was 0.020986. So 0.020986, and that's in seconds. And of course, our best estimate for the time and our best estimate for the x, our x was 7.53 centimeters. And our best estimate for the time was the average we calculated, and that turned out to be The average of those three turned out to be 0.128038. So uh, 0.128038. Of course, it was a lot of other digits, but we know that's plenty right now, and that's that's in seconds. So now I can say my fractional uncertainty in V is equal to my fractional uncertainty in X squared plus my fractional uncertainty in T squared square root, which is equal to in this case, we're going to take 0.01 centimeters and divide it by 7.53 centimeters, and we're going to square that. Plus, we're going to take 0.128 038 and divide it by our best estimate. Oops, I did it upside down. Let's kill that. We were supposed to put the sigma t up there, and I was reading the t. So the sigma t is 0.020986 seconds, and the uncertainty in t is 0.128038 seconds. We're going to square that. Now I can do zero point zero 0.01 divided by 7.53. And now I can square that. That, by the way, 0.01 divided by 7.53 is 0.001328021. I'm going to square that, though, and that gives me 0.000001, and then 763, and then 64. And that has no units. And then the other value, 0.020986 divided by 0.128 or excuse me, 128038. So 0.020986 divided by 0.128038. That gives me 0.163904,466. Now I got to square that, and that gives me 0.026. Now I'm going to go 864, and let's do a couple more digits. Let's call that 67. So that has no units as well, so I'm just going to add this 0.026 to 0.10000017. 6364. So I'm adding the 0.0268647 and the 0.00000017636, and that gives me the square root of 0.026. Sorry about that. 0.026,866, 438. So way more digits than we really need. Now I just take the square root of that, and that gives me a fractional uncertainty of 0.163910. So that's the fractional uncertainty in V, but as we found, the uncertainty in V is equal to the fractional uncertainty in V, which remember this is just a symbol, times the best estimate of V. So if I take the 0.163910 and multiply it by my best estimate of V, which is 58.810359 centimeters per second, I get a much more reasonable answer. So I'm going to say times 58.810359. And lo and behold, it turns out to be exactly the same answer. So we evidently did do it correctly. So it's 9.639 And I'll just call the next digit a 6, and that's centimeters per second. So that's another way you can actually do a calculation. Uh, Let me show you another propagation of error example. So for instance, we can do f of x, y, z could be like a volume where the width is x, the height is y, and the length is z. Then the partial of f with respect to x is just yz. The partial of f with respect to y is just xz. And the partial of f with respect to z is just xy. Now we can say the uncertainty in f is the square root of the partial of f with respect to x squared, sigma x squared, plus the partial of f with respect to y, quantity squared, sigma y squared, plus the partial of f with respect to z squared, sigma z squared, which equals uh, y squared z squared sigma x squared plus x squared z squared sigma y, sigma y squared. Let's make that a little cleaner. Plus x squared y squared sigma z squared. And that's the formula, but you can see it's not really pretty. I'm going to have to put in a lot of numbers. But again, if we use our trick, if we calculate the fractional uncertainty instead of the uncertainty, nice cancellations occur. So the fractional uncertainty, which is called sigma f over sigma f, is actually just the uncertainty in f divided by the expectation value of f. Well, the expectation value of f is just the formula x times y times z, where you're substituting the best estimate of x, the best estimate of y, and the best estimate of z. I'm going to take it and square it so that we can put it under the square root, so that now I have y squared z squared sigma x squared plus x squared z squared sigma y squared plus x squared y squared sigma z squared. So that's what we have under the square root. And now I'm taking f, which was x, y, z, and to put it under the square root, I have to write it as x squared, y squared, z squared. And you can see that you get a lot of cancellations. So for instance, the first term just becomes sigma x over x squared, because you can see the y squared in the denominator and the z squared in the denominator cancels the y squared and z squared next to the sigma x, and all you're left with is sigma x over x, both of which were squared. Same thing happens with this one. That's going to be sigma y over y squared, and the same thing happens with the z. The x squared and the y squared both cancel out with the x squared and y squared, and you're just left with the sigma z squared over z squared, which is the same thing as sigma z over z quantity squared. So that's another formula you could use. It turns out if you multiply and divide them, it still comes out to the same formula. So for instance, I could do f of x, y, z equals x times y over z, and I'd get the same formula. I could use f of x, y, z equals x over yz, and I'd still get the same formula. Or I could do yz over x and still get the same formula. So that's the beauty of the fractional uncertainty when you're dealing with multiplication. Uh, One other thing that might come in handy, for instance, we're going to learn about momentum, and momentum is supposed to be P is equal to mass times velocity. But that ultimately means you need an x component, which often is written px is equal to m times v times cosine theta, and py would be equal to m times v times the sine of theta. So what is the uncertainty in px? Well, that's going to be the partial derivative of px with respect to m. That's going to be squared and multiplied by sigma m squared. Then we're going to take the partial derivative of px with respect to v. square that, multiply that by the uncertainty in v squared, and then take the partial derivative of px with respect to theta, or we could do, say, for instance, with respect to cosine theta, but I'm going to do with respect to theta, and then I square that and multiply that by the uncertainty in theta squared. So the partial derivative of px with respect to m is just v cosine theta squared times sigma m squared. Partial of p with respect to v is just m squared cosine squared theta times sigma v squared. And then the partial of px with respect to theta is equal to m squared v squared. And now I'm going to take the derivative of cosine theta with respect to theta, and that's going to give me, in that case, because it's just one variable, the derivative of cosine theta is equal to negative sine theta. And then I got to multiply it by the derivative of theta. But in this case, we're doing it with respect to theta. So mv cosine theta, when I take the derivative of that with respect to theta, it's just negative mv sine theta. So I'm going to get negative, yeah, the negatives are going to, since we're squaring it, the negative will actually disappear, so I don't have to worry about that. But I do have a sine squared theta times sigma theta squared. So that's the actual formula you get when you're calculating the standard error in the x component of momentum, and that could be a mess. But again, let's look at what happens when we do the fractional error sigma px over px. So I'm basically going to take and divide the bottom by m squared v squared cosine squared theta. So this time it's going to get sigma m over m squared, because the v cosine theta both squared canceled out in the denominator. I'm also going to have, remember, m squared v squared cosine squared theta. So the m squared and the cosine squared cancels out in this case. So I get sigma v over v squared for the uncertainty, fractional uncertainty of the volume. And then this one's kind of weird in that I have m squared v squared sine squared theta is going to be divided by m squared v squared cosine squared theta. So sine squared over cosine squared equals tangent squared. So we can say plus tangent squared theta sigma theta squared. And of course, uh, the theta has to be in radians. The sigma theta has to be in radians. The tangent theta doesn't matter whether you put radians in or not, long as you put whatever angle you put in, your calculator is set on the right mode. Once it takes tangent, it'll just give you a pure number instead of a denominate number. But again, you can see how much easier and simpler the propagation of error formula is when you use a fractional error. And again, in this case, it was a case where we were multiplying three variables, or specifically multiplying m, v, and then the cosine of a third variable. So I hope that helps. I hope that gives you some understanding of how the propagation of error formula works. It appears no one showed up for our actual office hour, so I'm going to go ahead and call it a day. And sorry I didn't get to see anybody, but this will be posted in a few. Have a good one, everybody. Bye bye.